Multivariable calculus, we're looking at lesson 14.7, day 1. We are going to be looking at maximum points, minimum points, saddle points, and the saddle point might be the weirdest sounding part of this lesson. It's the idea of a maximum in one direction and a min in another. It says for a saddle point, the surface level's off, but it's not a max or a min. Let's take a look at this picture right here. It really can help us. We can have a local maximum point, very obvious. That might be a high point where Z is biggest in that immediate surrounding. The absolute maximum point means that Z is the absolute biggest. There will never be a bigger Z. And likewise, you can have minimums, local minimums, and absolute minimums. I think the saddle point is the one that sounds so funny. However, the saddle point would be right here where I've put a red dot. And you can think, well, gosh, why is that? Well, you need a maximum from one direction and a minimum from another. Let's just take a look. If we were on this green curve right here, that red dot looks like it's the lowest point on that curve. So we might think of that red dot as a minimum. That Z value would be smallest relative to all other points on that green curve. However, what if we went this way? And you can see that our green curve might look more like that. And our red dot, well, I made it green right here. That would be our highest point, our maximum, a maximum point. So really, that saddle point, it's really saying that you have neither a max or a min. It's not a max or a min, but it's a max or a min when you consider one direction over another. So saddle points are brand new. So we've got this function of two variables. Just like what we saw in single variable calc, we have critical points. And critical points, a point A comma B is a critical point if the derivative with respect to x of that point is 0 and the derivative with respect to y of that point is also 0, or if one of these partial derivatives does not exist. So that's very important. Once we have a critical point, just like we had in single variable calculus, we're going to have a way to test if our critical point is actually a maximum, a local minimum, or a saddle point. So here's what we need to see. That theorem in box 2, if f has a local max or a min, your partial derivatives should be equaling 0, or technically they could be undefined. But take a look. This is the critical part of the lesson, this green highlighted box, the second derivatives test. It's very formula based, and it's saying suppose that you found a critical point, that your derivative with respect to x, derivative with respect to y is 0. Then what you will have, and it's this formula right here, we're calling it D. It's almost like a discriminant. It's reminiscent of the discriminant that you had in Algebra 2, because you could have different cases, different occurrences with quadratics when the discriminant was a different sign. But this formula, we certainly don't have time to prove it. Second derivative with respect to x multiplied to the second derivative with respect to y minus f of xy of that point squared. If D is positive and the second derivative right here is positive, then that point pertains to a local min. Guys, this is reminiscent of what we had back in our single variable calc. Just want to draw this over here again. Second derivative being positive last year in single variable calc, you would have thought, oh, that means my curve is concave up like a cup, and you'd have a shape that looks like this. And of course, you would remember that a point there would be a low point. That would be a local minimum. That's not a bad way to help you remember what's occurring here. Likewise, if this d, if you want to call it a discriminant, you may. If that's greater than 0 and your second derivative is negative, well, you might remember we were thinking of that as concave down like a frown in single variable calc. Well, if that were the case, such a point would yield a maximum. That would be a local maximum. Look at case C. If D is negative, you don't even test the f xx, that second derivative with respect to x. F of a comma b is a saddle point. It's not a local max or a minimum. So that's case C. And then by trichotomy, a D could be greater than 0, less than 0. It could equal 0. Let's make sure we've got this part into our notes. If D equals 0, this is inconclusive. This is DKJD. We don't know Jack Diddley. So that's really the situation where if D equals 0, we're going to need something else to help us. And we will continue talking about ways to get extrema. But let's jump into example 1 and see what's going on. Here's your F. I'm going to come over here and find F, the derivative with respect to x. It looks like we will have a 4x cubed minus, well, the derivative of y to the fourth is 0, minus a 4y. And likewise, let's go ahead and take a derivative with respect to y. You'll see you get something amazingly close. You'll have a 4y cubed minus, in this regard, it's going to be 4x, won't it? Because, as we take this derivative right here with respect to y, we'll have a minus 4x. And the derivative of 1, of course, goes to 0. Well, to find critical points, we're going to set these equal to 0. And then we solve. And guys, we can certainly solve via our TI-89. But sometimes we do that so much that we can lose some basic skills, and I don't want that to happen. I'm going to divide by 4 on both of these. And then, look, I'm going to add a y here and say y is equal to x cubed. And then I'm going to substitute that in over here. So instead of writing a y, we'll write x cubed. This becomes x to the 9th minus x. And we can factor out an x. And it won't take you too long to see x could equal 0. This equation right here would become x to the 8th minus 1 equals 0, or x to the 8th equals 1. Here you've taken positive negative 8th root. You'd get x is plus or minus 1. But we're going to have to go back to our original equation to find what's happening when x is 0, when x is 1, and when x is negative 1. Guys, if x is 0, let's just do a little bit of work here with our critical points. Let's see, we're going to get very quickly a 0 very quickly over here. Oh, you know what? Pardon me. If we just solve this system, my goodness, we're not plugging in to get a z. But if we let x equal 0 right here, of course, y would equal 0. If x was equal to 1, of course, our y would be a 1. And if x was negative 1, then y would equal negative 1. So we've got 3 critical points. Later on, we can actually find out what z values are. Of course, to find a z value, you need that y value. And that's why we've got this system set up. So guys, now we have our critical points, but let's go ahead and see what's going on here. We really need to get a second derivative with respect to x. That was right here, and if we take one more derivative with respect to x, you can see we're going to get 12x squared. If we take a derivative of y, yet again here, we'll do one more derivative with respect to y. We'll get a 12y squared here. And then if we wanted to find f of xy, We can go back to this first derivative with respect to x, but now take the derivative with respect to y, you will get negative 4. And guys, right now we're going to build ourselves a little table, and this table is based off of this yellow box up here. So I'm going to make a little table here, and we're going to say we need our critical point. We're going to have this discriminant. And I'm just copying that from this yellow box right here. We're going to have our second derivative with respect to x right here, and then we'll have our conclusion. And tell you what, we are starting with the critical point 1, 1. Let's just do that. Well, when you plug in x equals 1, y equals 1, well, 12 times 1 squared, that's going to be a 12. The f, y down here, plug in a 1, that's going to be another 12. And then we're going to say minus, well, this f of x sub y is just negative 4. You know what? I'm going to move this over just a smidge. And you can see this thing right here, that's 144 minus a 16. The bottom line is this is positive. And when I plug in a 1 into the second derivative, it is positive. So this is really going back to this box where it's letter A, where we're going to say our discriminant was positive, our second derivative with respect to x is positive. You know what we're thinking of. It's looking something like this. So we're going to have a local min. We've got a local min. And we can say a local min of something. Well, this is where we can come back to our function right here and say f of 1, 1. Well, it's 1 to the 4th plus 1 to the 4th minus 4 times 1 plus 1. Well, that's 1 plus 1, that's a 2, minus a 4 plus a 1. That's 3 minus 4. That's going to equal negative 1. So it's a local min of negative 1 at this point 1, 1. We found a local minimum. Well, guess what? We're going to do the same thing with these others. Let's plug in 0, 0. And my goodness, the second derivative with respect to x right here, that's a 0. 12 times 0 squared. 12 times y squared, well, 0 squared, that's another 0. And this right here, that's a negative 4 squared. Well, you can see what's going to happen, guys. This is going to be 0 minus 16. That's negative 16. It's less than 0. This means we've got a saddle point. We've got a saddle point. And guys, if you're going to plug in 0, 0 into f, well, the x, the y's go away. You're left with a 1. So we're going to say it's a saddle point at 0, 0, 1. It's neither a maximum nor a minimum. To wrap this up, now we plug in negative 1, negative 1. Guys, very importantly, look at f double x and f double y here. 12 times negative 1 squared, well, it's still a 12. 12 times negative 1 squared, it's still going to be a 12. And we still have this right here. Guys, if you're really looking and paying attention, this is exactly what we had. 144 minus a 16. You don't even have to work that out exactly. That's positive. But then look at the sign of f sub double x. Well, 12 times negative 1 squared. Well, guess what? Negative 1 squared is positive. This is positive. This is going to be a local min, just like our first step here. So look, now what? Well, we're going to plug in negative 1 for our x and our y. And I think you can see what's going to happen as we're finishing this up. It's negative 1 to the 4th, negative 1 to the 4th, minus a 4 times negative 1 times negative 1 plus 1. This is a 1 plus 1. This is a 1 times negative 4. That's a minus 4. you can see it's also going to equal, just like we had before, -1. Local min of -1